Welcome to Lab 3 Recitation. So in Lab 3, what we have you doing is implement this crash safe log. And for a bit of context, the motivation behind this is like threefold. First, these logs are kind of cool. They're a common tool used in write-ahead logging to simulate these atomic transactions. So we want to commit a transaction to databases. We'd write to a log first and then simulate this idea of atomicity. The second point is that we wanted you to start reasoning about crash safety. So this lab introduces you to that. And the third point is that you notice that we gave you significantly more creative freedom in this lab. There's a lot less guidance in terms of what you'd have to do. There's no helper definitions. And part of this too is for you to figure out how you would write these definitions on your own. So to that end, in this recitation, I'm going to take the style of walking through how I would approach this lab as a student myself. Rather than just telling you exactly what to do, we're just going to work through, like, I have this assignment, what do I do? So the outline is that we'll start fairly high level. We'll start with looking at the logging API and how we would implement this at a high level, then some pseudocode. And then I'll spend a bunch of time looking at how do we concretely translate this idea to Coq. And finally, Tage is going to present the solution for lab 2. Okay, so the first thing we would do is look at the logging API. So this is our spec. So the definitions for what we have to do are in this log API.file. And the first thing we note is that, well, the state is just a list of blocks. This is a little bit distinct from the disk previously. Even though the disk, under the hood, the disk is also a list of blocks, the abstraction of the disk is that it has a finite size, whereas this log potentially has an unbounded amount of size. Then there's 3 operations. We have the get. Then what we would do is just read this post condition and say that.
Sorry, Stella, could you turn off prettify symbols mode?
This?
In your Coq buffer?
Yes. Do you know the command for that?
Meta X prettify symbols mode.
Okay. Sorry about that. Anyway, suppose that our log is consists of these 3 elements. Then our get operation would return this entire log. So it says that we return this entire log in state, and the state is unchanged. So return all elements. Okay. The next operation is the append. And this is probably the most interesting operation. We'll take a look at this post condition. And there are 2 options. We can either, list of blocks, return true or return false. Suppose we want to append this list of blocks to the old log here. If we return true, the new log is the old log appended with the new log, set of blocks. And then if we return false, the state is unchanged. So the idea behind allowing these 2 options is that, remember that the disk has a finite size, but the log itself is potentially, the abstract specification state is potentially unbounded. So if we try to write too many blocks, your implementation is allowed to return false. There's a bit of a loophole here that you can observe, which is that your implementation can technically just return false and do nothing. And this is a perfectly valid implementation, but basically do not exploit this. You're not going to receive credit for doing this. Lastly, the interesting part here is that we might crash while doing this append. And if we crash, it's atomic. So if we crash, either the new state is equal to the old state, or we've successfully done the append and it's equal to the new state appended with the, it's the old state appended with the blocks appended. So the tricky point here to note is that this append will probably require multiple writes. And our underlying disk only has atomic single writes. So somehow, while we do these writes, if we crash in the middle of them, somehow that can't be visible. Okay, and the last operation is the reset. And this is fairly straightforward, just empty the log, except if we crash again, either where the new state is the empty log or the new state is still the old state. So we can't have an intermediate crash where we just like delete some blocks and there's some state in between. Great, so let's move on to the implementation. So we implement this log on top of the one disk API. This is actually the same thing you did in lab 2. So recall that the one disk API has, the state is a disk which has some finite size, and we give you atomic reads and atomic writes. But these are atomic single writes. So the problem is that append requires multiple writes. And if we crash in the middle of it, our specification says that we can't be stuck in some state in between. The typical solution for this is that we'll store a header. So let's see, get a picture of a disk. This is our disk. It has some of the fixed sized. Let's say our spec state is this. The typical solution is to store the log size in the header. So why does this work? Well, first let's think about how get would work. What get would do is read this log size, 3, and then it'll read the next 3 elements of the disk. So you can observe here that, you know, there could be complete garbage in the rest of these blocks, but we don't care, because our get operation will just look at the next 3 elements and ignore the rest. And our abstraction relation needs to capture this idea that the first block, so let's see, the abstraction relation needs to capture the idea that first block contains the log size of the specification state, and the next like n blocks where n is the log size contains the log. And the rest is don't care. So now that we've figured out how we want to implement our log using this one disk API, let's try to reason about why is this crash safe? So how does append work? Let's say we have our disk here, and we want to append C1, C2, and C3. What are we going to do? We're first going to write the first element C1. Then we write C2, C3, and then finally we update the size here. So the idea is that at any point here, we can crash, or we can crash there, or there, or there. But if we crash at any point here, we're fine, because this log here is still the initial log. So we're still related to, this is like, let's say this is logically related by our abstraction relation. We're still related to the original log, and it's same here, same there. And here is when we commit. So this is the point where the append logically happens. At any previous point, we're still related to the old state, and it's only when we do the singular write to the log size that we reach the new state. So one of my favorite diagrams to look at is this diagram here. So here, this is the specification state. And this is our implementation state. There's also some garbage, or there's some extra space, but I'm not showing it here. So this picture generally just says that whenever our implementation state is related to a specification state, in this case, there's only one possible state here that it can be related to, which is like B1, B2, B3. So I'm just writing that there. And if we do an append and return true, we end up in this state. There has to exist some spec state, but our specification already told us that the spec state has to be this new set of blocks. So the subtlety here is that at any point we might crash. And every time you do a step proc, remember that there was like some exist condition where you had to prove the recovery condition hold and like we were still related to the specification state in some way. So let's take a look at what that looks like. If we crash here, let's say we're stuck on this state. The spec says that we have to either be our old state or our new state. So to just like informally reason about why this is crash safe, we know that in this state, we are still related to our old state. So we can like write this right here and then it's safe. So this is like the high level overview of how this works. The last operation is the reset. So regardless of the state of this log, if we want to reset, we need to do this atomically. And the easy thing to do is just write 0 to the header. This works because this becomes logically related to the empty state, which is exactly what we wanted. And it's an atomic operation. So if we crash, it's still, if we crash before we do the write, it's related to the old state of B1, B2, B3. And then if we crash after, it's still fine because related to the new state. I'm going to briefly pause to see if anyone has any questions at this point. Okay. Let's continue on to the pseudocode. How do we actually implement this get and append? So remember, this is our block here. To get intuitively, what we want to do is, well, we first want to figure out the header size. So size is equal to read header. And then we want to loop over the next number blocks and probably write them in some accumulator and return it. So we might go like for I is equal to 1 up to size plus 1. We'll read this block, read block I. And then we want some accumulator that accumulates the blocks that we read. So we'll write like accumulator is equal to accumulator plus a block. And then we return the accumulator. This is fairly straightforward. The tricky part is that whenever we have a loop, we're probably going to need some recursive function. But luckily in this lab, we implemented some loop combinators for you. And I'll show those later when we get to the clock part of this recitation. Now let's look at append. So suppose we want to append C1, C2, C3 to our disk. There's two cases to consider. Either we're out of space, then we return false. Otherwise, we're not out of space and we need to figure out where to start writing. So our disk size is 3. And we'll start writing at index 4, which is size plus 1. So let's say our starting index is size plus 1. Then for each of the blocks in this set of blocks here, so for block in blocks, I'm going to move this diagram down. What we're going to do is write block at index, and then, so index is 4, we write the block, and then we increment our index. Great, so index is 5, we write this block there, and then we write this other block. Finally, the last thing we have to do is commit. So to commit, we need the new length. So let's say our new length is the size plus the length of the blocks that we want to add. So the commit is writing new length at the header. And then we return true, because we've already reasoned that we have room to do the append. Okay, so let's also finish this part here. When do we know we're out of space? Well, we're out of space if the new length plus 1 element for the header is greater than the disk size, basically. So this is the entire pseudocode. And again, we have this for loop here that we're going to have to reason about and implement in Coq. So now I want to spend a bunch of time just looking at how we translate all of these ideas into Coq. Like this pseudocode is fine. I think the confusing part is often just like, how do we write this stuff in Coq? So let's move on over to our implementation. Let's see. I'm going to change. Okay. So the first thing we note is that we're implementing a log on top of this one disk API, and our log follows this logging API. Then we have to implement these 5 operations. We have to implement our log abstraction. We're going to have to show that our abstraction relation makes sense. So this is saying that if the header of the block is 0, saying that there's 0 blocks that's related to the empty list. Here we're saying that we can ignore the extra garbage, because if the header is 0, it's still related to the empty list. And here we're saying if there's 2 blocks in a log, we only have to look at the first 2 blocks and we could ignore the rest. And then we're going to have to prove that our implementation is correct. So just walking through this, I'm going to take a brief detour with init. The idea behind init is that you want to initialize your disk to something that matches, something that is a valid log. And what you're going to end up doing is defining your initialization procedure. And then you're going to first call the underlying disk's initialization procedure, and then you're going to call your own initialization procedure. So probably what you want to do is initialize your disk to the empty log. And you'll also have to reason about the case where, what if it's not possible to initialize my disk to the empty log because maybe my disk is too small? So recall that you can return 2 different values. Let's see. You can return either initialized, or you can return init failed if you aren't able to initialize the log. And you should just look at your implementation for lab 2. So to look at get, we can start translating get to cock. You can imagine that the first thing you would do is, well, we're going to read the header. So let's say that the header is some address and it's equal to 0. Then we're going to write, well, the size is, we're going to read the header. And then somehow we need to implement this loop abstraction. So there's different ways you can do this. One way is to write your own fixed point, but we haven't done this previously in the lab or in the previous lab. So what you might want to do is recall in lab 1A, where we have a bunch of loop combinators. We have 2 loop combinators. Let's see. We have the for each, and we have the for range. So what does for each do? Oops. It takes a list of blocks, or values v, but in this case, I'm just going to say it's a list of blocks because this is the way we're going to use it for append. And it takes some body, which has type body to some t. So when you look at t, you should just think of it as your accumulator type, which in the append case, we can see that the accumulator is this index variable probably, which is a natural number. And it's some procedure that returns this act type. And then it'll also take an accumulator here. And what it does is that for each element in the list, we'll run the body of the loop with the new accumulator and update the accumulated value. This is the one that we'll probably end up using for append. The next thing that we have to look at is for range. So how do we figure out what this does? Well, there's some starting index, and there's a count, and there's a body. So the start tells us obviously is an index of where we start. And what this combinator does is that it runs the body count number of times. So the count is the number of times to run the body. And here the body takes the natural number, which is the index where we want to run the body, the accumulator type again, and it returns the accumulator type. And it also takes your starting accumulator. Okay, so we have this loop combinator. Now how do we write get? Well, let's think about what we have to do. And let's actually just work through an example. So let's say our disk consists is this, let's use this notation. And then we want to do get. So the first thing we might do is read block 1. First of all, our accumulator is empty. We're going to start at index 1, presumably, because that's where we start reading. And how many elements do we have to read? Well, we're going to read the size number of elements, which is 3. So the first thing we do is, well, we're going to read at index 1. And then we're going to add this to our accumulator. So now our accumulator is this thing right here. And then we're going to increment our loop. So now we're going to start at the next index, which is 2, and do this 2 more times. Let's run through the next part of the loop, read B2, and now we add this next element to our accumulator. And we decrement our count. Finally, we do this one last time. Our count is 0, so we're done iterating through the loop. So this translates very nicely with our for range. So you can imagine that we're going to run for range. It's going to take some starting index, some count, some body, and some initial accumulator. Well, we know the starting index is going to be 1, so we can fill that in. We also know we're going to run this count number of times. This is probably going to be something like size here. And then we know that our initial accumulator is the empty list, which is nil. And we're going to return this accumulator right there. So usually what I do here is write a separate definition for what this body is. And the very first thing you do usually when writing a definition is figure out what type it has. So we knew from before that it has this, it takes a index, which is of type nat. And then our accumulator type in this case is a list of blocks, because that's what we're accumulating. And this is a procedure that returns a list of blocks. Great. Now that we fill this in, we can try to see if Coq is happy with this. It's not. The problem is that, here, I'll show the error message. Size has type block while it's expecting type nat. So what we read is a block, but what for range expects is a nat. So we have this block to address function that you can use to switch to translate this. Okay, so just so that I'm not giving away the entire solution, can anyone tell me what I should write for get body?
I guess it should read what is at the index.
Yeah. And then what?
And then you can add it to the accumulator.
Yeah, exactly. So that's exactly what we want to return. Let's say we read B1, and then we just add it to our accumulator right there. So now we've successfully implemented get. Basically, you're going to want to do the same thing for append. And I might come to this, back to this after. Actually, let's start doing append, because why not? So what do we have to do for append? Append has a different loop, which is the for each loop. And I'm only going to do the loop part, or demonstrate the loop part. You can imagine that what we're going to end up doing is looping over each block. So append helper is going to take a list of blocks. And it's going to take some starting index here, which is a natural number, or an address, I guess. And it's a procedure that's going to return the accumulator type, which in this case is the index, which is of type address. And what you end up having to do is, well, okay, for each, the first argument is the list of blocks that we give it. It's going to take some body. And it's going to take the starting accumulator, and it's going to run the body on each of the elements in the block. I will let you figure out what to do for body yourself, but intuitively, the idea is that, I guess we could work through an example actually, what this looks like. So your disk is that, and you want to append B1, these three elements. So our starting accumulator is 4. We're starting to write at the 4th element of the block. And the first thing we're going to do is we'll write at 4 C1. And then we're going to update our accumulator to 5. So remember, this is like the index is equal to index plus 1. And then what's the new state of our disk, just so that we can see it? Now it contains C1. In the next iteration, write 5, C2, accumulator 6. And etc. So you sort of get the idea that your body is just going to do exactly this. It's going to write the block to the index, and then it's going to return the updated accumulator, which is just the index plus 1. Something to note here is that I think there's two things to note. One is that when you write the new length to the header, you need to convert an address or a natural number to a block. And this is a procedure, so you'll have to end up writing like new length is equal to address to block something. And it's not a Galena function, so you can't just directly write it the way that we wrote block to address here. The second thing to note, which I think someone else ran into, is that you'll need to somehow check if we're out of range here. One function to do that is to do greater than dec. So like if greater than dec, new lane plus 1, disk size, that would work. But you'll run into something weird where if you just directly write return, you'll get an error. And the problem here is that greater than dec is not a Boolean. Whereas there's like less than, you can instead use less than Boolean, which returns a Boolean. And it's a bit of a weird Coq thing where Coq doesn't really know the difference between this and a Boolean and a real Boolean. So this is just like a side note. It's not very important. It's just kind of a cute Coq thing. Or I can write and it treats this like foo variable as true, whereas if I write bar, it'll treat it as false. It doesn't know the difference because a bool is just like an inductive with 2 constructors. But anyway, this is really not important. So the next part you have to do is the abstraction relation. I think we've gone through enough examples where we sort of know what we have to do. We have to like reason about the first block contains the size of the log. And also we have to think about how do we talk about that the first 3 blocks here matches the log. So like, let's say we write this function, disk matches list, that takes a disk. and a log. So there's different ways you can write this function. One way is to use this disgets. So what does disgets do? Disgets takes a disk D, it takes the starting address, and it takes some number of blocks, and it returns a list of option block. So it's just starting at the starting index and reading n blocks. You basically want to say something like, disgets D start count is equal to log, where like you have to figure out what starting count are, obviously. But this equality won't work because there are different types. So log is a list block and disgets returns a list of option blocks. So what you can do is use this maybe equal list thing to express that. So instead you would write like maybe equal list, this thing here, that. So in your lab infrastructure, you might see this symbol instead. And this symbol just stands for maybe equal list. If you don't like the symbol, you're very welcome to just comment out the notation. Or you can like remind yourself of the definition by just writing print and that notation is going to tell you that, well, this notation stands for maybe equal list. Brief pause for any questions, if anyone has any. Okay. So the hardest part of this lab is probably figuring out get and append. Recall that when we wrote get and append, we use these loop combinators. And whenever we have these loop combinators, we need to figure out how to write loop invariants for these combinators. So actually, because to demo this, I need to have some value here. So I'm going to do the trivial log abstraction relation. This is obviously wrong. We have you first proving get because this is the best way to check that your abstraction relation is correct. The problem is that right now, if my abstraction relation is wrong, I can actually prove that my append implementation is valid even if it's not. But if we first do append, we avoid this issue. Okay, so let's start off our proof. And it's a bit messy on the right, like you can see. So usually what the first thing I would do is just like write simple here. So this should be like very familiar to you guys by now, which is saying that our precondition is that our state is related to the spec state, and our postcondition is that there exists some spec state, and we actually say that that spec state is the same as the old spec state, and return the old spec state here, and the log abstraction holds. Let's see. So as is usual, we start with doing a step proc. Trying to figure out why I can't do step proc here. I think we need to implement the recovery procedure. So I skipped mentioning this. One of the questions that we often get is like, well, what do we do for recovery? So the idea of the recovery procedure is that if our dish crashes, we're allowed to run some recovery procedure. In this case, we don't need to do anything because we've already reasoned about our log, and we know that our disk is crash safe. It could crash at any point. We don't need to run a recovery procedure. But we do need to call the underlying disks recovery procedure. Basically, what I would have done is just like look at lab 2 and see that this is what they did and probably do the same thing. Okay, so now we're back here and we do step proc. The first state corresponds to the recovery condition. So remember, every time we take a step, we need to look at our recovery condition and see if we're able to show that, see if we can give a spec state such that this holds. So our state is the same and the log abstraction still holds. This is obviously true. It's just the same state. eAuto solves it nicely for us. Now we have this like for range here, and I might try to do a step proc, but this doesn't work. And the reason here is that step proc doesn't know what to do for range. So if you recall from lab 1A, what we end up doing is writing a bunch of helper lemmas for this. And in lab 1A, we kind of gave you this off the, we already gave you this, whereas now I'm trying to give some intuition for why we gave you the lemmas that we gave you. So what we would do is let's look at logging API. We have this for range theorem. And this for range theorem gives us a way to write specifications describing the behavior of for range. And this is basically a theorem that helps you do your induction. The idea is that we have this for range spec where we have some loop invariant in the base case. And the post condition is that the loop invariant still holds after count number of iterations. And the crash condition is that we must have crashed in some iteration of the loop. So there exists some number of loop iterations that we did, n, where and n has to be less than the number of times we do the loop. And this invariant holds in that state. So the way this works is it's kind of like a slightly weird way of doing induction, but the idea is that proc spec will say that your base case holds because that's the precondition of for range spec. And then this part here is saying that, well, if it holds in the first case, then if this invariant still holds after we do one step for all n, then this is like the standard induction. The loop invariant holds after we do n steps, as long as like n is less than the number of steps that we actually wanted to do. So what I would do here is like copy this over. And I know that I'm probably going to write a helper definition for this. So let's see. Helper OK. And it's going to take the form of, let's try to match these up. Our starting state is 1. Our count is blocked to address R. Well, really what we want to do is like generalize this and do this for like any count. And our body is get body. And our accumulator is the empty list, nil. And this is our abstraction. And let's figure out the specification. So the starting state, as we already decided, was 1. This is fine. And our accumulator is this right here. The tricky part, of course, is figuring out what to write for this loop invariant. So for this, we need some like intuition behind what we want this invariant to be for get. But the first thing we're going to do is like, let's just look at what the type is. So looking back at this specification here, the loop invariant takes some index, some accumulator type here. Actually, let's look here. It takes some index. It takes some accumulator type. This is a go state, which I'll go into in a bit. And it takes the old state. And the post condition is that the post condition talks about the new state. So with this get helper function, you know, what we want to do is like, how do we want get helper to behave? We want to say something like, let's see. Well, we imagine that like state prime is equal to, it's unchanged. And after we do like, after n iterations, if the accumulator is like some list of like, I don't know, B1, B2, somehow like this disk should match the accumulator, or we want to say something like this. So you'll notice that in the post condition, there's no way of talking about the previous state right now. But we do want to say that, you know, after running this loop, we didn't change the state, because otherwise, you know, we can't reason about our get function being correct. So this ghost state here basically lets us do this. Ghosts are scary, but there's nothing scary about ghost states. Ghost states are sort of like Casper the Friendly Ghost. Anyway, so what you'd end up doing is basically passing your starting state as the ghost state. This lets us talk about the invariant using the this lets us refer to the starting state in both the precondition and the post condition. Okay, so let's sort of write this out. This is our type. And we're going to write some loop invariant. And it's going to have like some starting index. It's going to take an accumulator, which is our list of blocks. It's going to take our ghost state, which actually is just the starting state. And it's going to take the new state, and it's some prop. It turns out that you're going to want to also pass in the count. We have this information here for this entire, whenever we call get, there's like a constant count for every time we call get, which is just like the number of elements we wanted to get. And then we fill this in right there. Okay. Let's move that up there.
Stella, you might need to explain currying at this point. I don't know if we've seen that.
Yes. So you'll notice here that I just applied one argument to get invariant. What this does is that, like in functional languages, because get env takes multiple arguments, I can sort of just partially give it an argument. And then if I have something here that's like, maybe the invariant is that start is equal to count. This is obviously wrong, by the way. Then what I'd end up doing is like getting a function where if I pass in a particular count, like let's say it's 4, then start will be just like specialized to 4 here. Yeah, is this confusing for anyone? Okay. So what I would do here is like, I have this, yeah. So just to like show you how to debug this error, this is a common error with like notations where it doesn't know how to like parse this all together. The first thing I usually do is just like put parentheses around it, and that usually works. Or you can write a nil, and that would also work. So the one other thing that we haven't talked about is this wipe here. For the purposes of this assignment, I think you can safely ignore wipe. So what wipe does is, it says that, you know, after we crash, we're allowed to like, in the middle of the loop, we're allowed to do it's a relation between the state, the previous state and the final state. For our purposes, we can just like say that the we're not running any recovery procedure. So we're just saying that like the next state, the state prime is just the same as it was before the wipe, which is just like this no wipe thing. Just to show you what that is. It's just saying like the states are the same and there's like nothing to really think about here. Okay. So to check that I got this correct, one of the first things I'll end up doing is like, see if that solves my step proc being stuck problem. So you have to add this to your hint database so that step proc knows about it. And then I can try to do step proc here. And okay, it goes through. I'll show you what to do with that later. Then I try to prove this. Oops. And I might try to do step proc. This won't work. It again doesn't know what to do for range. But recall that we had our for range OK function, or lemma, sorry. And what you end up doing is just like, first I need to do intros, apply for range OK. The first is just a recovery condition. It's going to say nothing. I'll just like quickly show that. Oops. Yeah, it just says the state is unchanged, et cetera, et cetera. Not very interesting. And the second is that loop induction step that you're going to have to prove, and you did a similar thing in lab 1A basically, where you have to prove that after iterating one element in our loop, the invariant still holds. So just very briefly, what does this look like? This is the recovery condition. If we crash, everything is fine. Let's omit this first one. And this one is saying that the invariant for doing one more iteration still holds, given that we knew that it held previously. Okay, so what you should do is probably just like refer back to your lab 1A solution to see how you've did this. The last point I wanted to talk about was that we talked briefly about ghost states, and like after doing the step prog, I have this like big ugly block to look at. So this is like really nothing scary. What you really have to like just to pay attention to is that it's asking you to give it a ghost state A0 such that this like invariant holds and all of this is great. Remember that we said that our ghost state is just the starting state. Oops. So what you would end up doing is just writing like exists state here, starting state, and then like simplify. And then suddenly that big ugly block goes away and we get something nicer to prove, which is that like the invariant holds for a base case, something about a recovery condition, and then we have the rest of the procedure, which is just a return. Okay, I'm gonna spend 5 more minutes and just like briefly talk about your task for append. So append, you're going to go through the same process that I just went through of breaking up the 4 ranges and like finding the loop invariants. The loop invariant for append needs to talk about, a little bit about what happens after I do like 2 writes. So let's say that I just wrote this, and then what is my new state? So like remember in our go state, we're going to have like, you know, we're going to have an invariant that has both our old state and our new state. And somehow your invariant is going to relate the two by saying that state prime is equal to state after doing a bunch of updates. Updates, in this case, C1, C2. So we have this function disk upds that you can use, which basically, let's see what disk updates does. It takes a disk and a starting place to do the writes, and it takes a list of blocks to do the writes, and it just like updates, it does the writes starting at that index. So you might find this helpful. You're welcome to define this for yourself. Yeah, so this is all I wanted to talk about for lab 3. Are there any questions about any of this? Okay, if not, I'm going to pass it over to Tage to talk about lab 2 solutions. One more note for Append is that in lab 2, we wrote these like remapped abstraction, like no disk, like update lemmas for you. While you do Append, you'll end up having to reason about like crashing at every step, and it might be helpful to write these lemmas for yourself. So you like end up in a case, and rather than like ending up with one monolithic proof, it's useful to just like factor out lemmas so that you don't have to like duplicate them for every case. Okay.
All right, thanks, Ella. Okay, so what I thought I would do is I'm going to go over a little bit of the lab 2 solution just to highlight some conveniences in Coq and sort of highlight how, illustrate our process for going through this so that you can use this in labs going forward. So part of this is to make I'm hoping to make your life easier by giving you some tricks that make your proofs more concise so that the development flow is a little bit faster. Okay, so the first thing is just so that you have the context, because your abstraction relation may have been a little bit different from the staff solution. I'm going to show our abstraction relation. So the way we wrote our abstraction relation is with 2 fairly simple conditions. So as you probably noticed, you need to use a for all in order to state some property about the good blocks. Our statement about the good blocks, first of all, it says for all addresses. So first of all, the overall form, which hopefully you discovered at some point, is we have for all A under some conditions that if those conditions hold, that implies some equality. So if you look at the equality, if you look at this conclusion, we're saying that the 2 values match. The abstract state, which is the RD disk, matches the disk in the bad block API at address A. Now, this doesn't hold for all the addresses. In particular, it's not true for the bad block. And it's also not true for this little edge case, which is the last address in the abstract state. Sorry, not the last address, the one that's just past the end. So recall that the last address is disk size -1. If we're reading exactly 1 past the end of the abstract disk, then what's going to happen is this is going to be in bounds, sorry, this is going to be out of bounds because this disk is smaller, while this disk is going to be in bounds. It's going to have the remapped value for the bad block. So this equality can't possibly be true, 1 past the end. The bad block is kind of similar. We state that the remapped block is correct, but note that this is not going to be true if the bad block happens to be the last block. So this is a weird case that you need to think about, at least for the sake of the abstraction relation, which is that if the bad block happens to be the last block, then there's actually no remapping going on. Every address is being mapped exactly, except that the bad block, which is the same as the last block, is not part of the abstraction, is not part of the abstract state, but it is part of the code disk. So we just put in this conditional statement so that this only holds when the bad block is actually distinct from the last one. Okay, so I'm going to skip over these example theorems. The example theorems are actually a little harder to prove than you might expect, just because the tactics are a little bit annoying to deal with. But I will go to our init OK proof. So our init OK proof, oh, 1 second, clock is being slow. Our init OK proof is not that long, but it has one big case that's somewhat complicated. So we do some step procs to get over, just to step through the basics of this function. Our init procedure checks whether I think it's checking whether the size of the disk is too small, or it's, I think it's confirming that the bad block is inbounds or something. Then here's a problem that you probably ran into when you were doing your proof. You want to access the value stored in the last block in order to construct the abstract state when we start off the system. You know that this is in bounds, and therefore we should be able to get an actual value for it. So the way that the proof goes is we use this kseek to consider whether or not it equals some block or not. And then just remember, so after you do this kseek, you get 2 goals. In one of them, we get some block, so that's great, we can use that block. And then just remember at this point that in the other case, we're gonna be proving a contradiction because H0 is instead gonna say that this diskget equals none. And we're gonna end up proving a contradiction there. Probably what I would have done when I was writing this proof is I would jump to that case first and just quickly do this proof because it's a lot simpler. Let me simplify this proof a little bit. So we're going to do this proof by contradiction. So there's this, you maybe have seen this X also tactic, which switches to proving false. So we're going to prove a contradiction. The contradiction that we're going to prove is this theorem disk inbounds not none. We might have thought, okay, we want to prove a contradiction based on the diskget being none. So I might have done a search that looked something like this. That returns a pretty small list of theorems here on the lower right. This theorem looks kind of similar to what we want, but it's the wrong direction. We know that diskget DA equals none, and from there we want to prove false. So disk inbounds not none is the one that we want to use. So it turns out that this is pretty easy to do with just doing E applied disk inbounds not none. Okay, so I guess like the simpler way to do this that we probably should have done in the solution, you can apply this in H0. That'll get us H0. That'll prove false, so we should be able to solve the first goal with auto. And then the second goal is an arithmetic goal, and so we're going to use Leah to solve it. This inequality is true, but for somewhat complicated reasons that Leah could figure out. Then I'm going to go back to this case where we did actually get a value. You probably had to write some expression that was fairly complicated. Even the staff solution has to write down this complicated expression. But then we were a little bit principled about how to handle each of these cases. And there are a couple tricks that make these proofs pretty concise. That's why this is only about 10 lines of code. First of all, we use simplify to just break apart these ands and to introduce everything. Then there's this tactic auto rewrite with upd. If you didn't discover this, then I'm sorry, you probably had to do this stuff manually. So let me first illustrate what you might do if you were not using auto rewrite with upd. First, we look at this goal and we see there's at the outermost level, what's going on here is there's a diskget of a disk upd. And if I follow the parentheses, this disk upd is at the bad block, and we're getting from A0. So I also know that A0 is not this value. I'm not exactly sure what this value is. So let's try simplifying this. So we can see here that this is a disk size of a disk upd. So let's first figure out what does what theorems are there already about the size after you do an update? There's only one theorem because the situation is very simple. Updates never change the size of the disk. So then what I would do at this point is I would rewrite by this theorem in H2 and make that a little bit simpler. Then we see that there's a disk size of a disk shrink. So you might do another search for this. The problem, of course, is that this quickly gets to be very tedious. So what we've done is we've given you a tactic, or really we've set up the auto rewrite tactic to automatically apply as many of these rewrite theorems as possible. Auto rewrite with update is carefully set up so that it never does false rewrites. So it's possible to do a rewrite which has some side conditions, some premise that isn't actually true, in which case you would be left with an unprovable goal. But auto rewrite with update will never go wrong in that way. What it might do, though, is it might fail to do some rewrite that is actually true because it doesn't know how to prove the premise. So in this case, auto rewrite with update makes a great deal of progress, but you can see that it still leaves these expressions like this diskget of disk shrink alone. It doesn't know, it was not able to prove what happens with this diskget of disk shrink, so you still need to follow this manual process. Auto rewrite with update will just save you from doing it all over the place for the really obvious things. So if we look at diskget of disk shrink, there's only one theorem, disk shrink preserves. So we rewrite by that. If we're able to apply that rewrite, then the goal becomes trivial. The left and right hand sides are the same. So that's why I just do the semicolon auto to prove the first goal without thinking too much about it. But in order to apply disk shrink preserves, we have to prove this theorem. So I'll skip over the solution. After that, we probably did one more search to figure out what disk size of disk shrink is. But I do want to illustrate, I do want to illustrate one more thing, which is this by Leah part. So let's say we found this theorem somehow by doing some search. This theorem has a premise, which is that the size of the disk you're shrinking is not 0. So let's say we just did disk shrink size, which is probably what you've been doing. Awk does two things. It does the rewrite, so it simplifies this part, but it also emits a second goal, which I call a side condition. So this is a premise for disk shrink size, right? This theorem has some assumption under which it's true. So one dangerous thing about doing rewrites is that if I just did this rewrite and then I started proving the first goal blindly, then it's possible that the second goal is actually false, and this rewrite was the wrong thing to apply. So to save yourself from doing that, one thing you can of course do is the same thing I did earlier, which is you admit the first theorem, the first part, and you move on to the second one and prove it first. So in this case, I think Leah is actually able to prove this, and it is true. So this whole pattern of having to admit the first goal and then move on to the second and prove it with some obvious tactic like Leah is pretty annoying. So there's a shorthand for all of this, which is you can use this by keyword and then some tactic. Often it'll be something like auto or Leah. And what this rewrite by does is it attempts to do the rewrite. And then if the rewrite spawns any side conditions, any extra goals, it attempts to prove them using this tactic Leah. If this fails, then the whole rewrite is going to fail. So I think auto is not going to work in this case, or maybe, well, it does in this case, but let's say we gave some nonsense theorem like idtac, which does nothing. So you can see now that this this whole tactic with the by, it failed. It said proof is not complete. This is actually a good thing. The reason why we want this is because we want to be told immediately that we're not able to, we didn't automatically prove the side condition, and so we should think through why we think the side condition is true, maybe change this tactic, or maybe we need to rethink what rewrite we're doing. So the upshot of all of this is that if these by tactics work, then you can be sure that you haven't turned a provable goal into a false goal, because that's the most dangerous thing you can do while proving. If you do that, then you're going to have to back up and see where you went wrong. If rewrite by succeeds, you know that you can move on safely. So we use that regularly. Auto rewrite with upd also does this. So auto rewrite with upd is guaranteed not to spawn extra side goals that might be false. And also we've gone through some pain to make sure that auto rewrite with upd results in strictly simpler goals and never makes the goal more complicated. Okay, so that's all I wanted to say for init. Okay, are there any questions at this point? Okay, so in that case, I'll move on to the second thing I wanted to go through, which is just a little bit of the read okay proof. So the read proof is a bit longer than the init proof. So in order to avoid getting lost, one of the things that we're very careful to do is I try to avoid step procs resulting in very deeply nested bulleting. The way that I do that, there's two ways you can do that. So if you don't want to use this semicolon chaining, or if it doesn't work, then what I do is step proc, you pretty much know, is going to spawn two goals. It's going to ask you to prove the recovered condition. It's going to ask you to prove the crash condition after every step. And most of the time, the recovery condition is going to be obviously true. So for example, right now it's true because we haven't touched the disk at all. In fact, read is a read-only operation, so we're never going to modify the state. And therefore, the reason why the abstraction relation continues to hold is because it held at the beginning. So that's why eauto just solves this goal. I could write something like this, and then after every step proc, I could prove the first goal by going into curly braces and using eauto. That's really tedious and annoying. And it makes the proof harder to read. So what we do is we just do semicolon eauto. This runs eauto on both goals generated by step proc, and eauto solves the first one, so that you never even observe that first goal. Okay, so after a few steps of that gets through all the functions that read is running. Finally, we actually return a value, and now we need to prove that the post condition holds. So the reason why I can tell that is because there's a marker that says post ret. So this is telling us that we're proving a post condition and we've returned R from the whole function. I can distinguish this from the recovery cases because in the recovery cases, you get a marker that instead says recovered condition. So the reason why we put in these markers is because sometimes if you're using these powerful automation features, then you can get confused about exactly where you are in the proof because you can forget exactly what step proc did. The first thing that we chose to do in the STAP solution, I didn't double check exactly why we did this in the solution, but I'm guessing it was just like a common manipulation needed, and so we just did it at the beginning, is we replaced disk size state disk state -1, which you can see shows up in H1, for example. We just replaced that with disk size state 2. So we want to uniformly use the size of the abstract disk. The replace tactic has the same feature as rewrite. This by Leah ensures that this replacement is actually correct. So if I had made a typo, like let's say I had done this instead, replace will, let's say I had gotten confused and I wrote the code disk here instead of the abstract disk. Replace is happily going to make that replacement, but now the first goal is probably unprovable because these things, the first goal I can start working on, and I may or may not be able to prove it, but it doesn't really matter because the second goal is false. So again, to avoid this kind of danger, you can just use by Leah because you think that this replacement is obvious, and it will specifically tell you that it's not obvious, or at least Coq can't prove it, which can help catch mistakes before you go off and assume them too much. many people, when they first see these exist goals, they get confused about what the abstract state should be. You can usually just read this off from the goal, right? So the specification in this case tells us that the new abstract state has to be the same as the old one. Again, this is a read-only operation. It shouldn't be changing the abstract state in the same way it's not changing the code state. So in those cases, you can easily say exist state 2. That's the only possible choice that would work. And you should be able to use this simplify and auto tactics to solve the simple parts of this, right? So simplify is going to break it up into a few sub-goals, and this one is obviously true, and this one turns out to be obviously true because you have all of remapped abstraction in your hypotheses. One thing that, okay, so I want to give just the overall sense of what we did in this proof. So really, we just did two things. There are really only 4 cases here. First, we have to consider this read okay. First, we have to consider whether or not this is true. So one sec, let's indent this. So the read has 2 cases. So the proof is clearly going to have at least 2 cases. The first case is the one where we're reading from the bad block. That's this R equals A case. And then the second one is the sort of the normal case where we're reading from a good block. We're reading the same address because it hasn't been remapped. Okay, so if we look at the proof, it has close to that structure, but there's a little bit more case analysis that we did in the proof than in the code. So the code has 1 branch, and so the proof clearly has 2 branches. Sorry, the code has 2 branches, this one if condition. And that corresponds to these bullets at line 237 and line 259. Probably if I were a good person, I would have written some comments here saying that this is the reading from the bad block case, and this is reading from another block. If you look at the proof, there's one more destruct that sort of comes out of nowhere. So I want to explain why that case split is actually natural and how you could have come up with the idea to do this destruct. So what's going on here is where the code is going to read from the bad block, sorry, from the last block, because that block has been remapped. The user is reading from the bad block, so the code is going to turn around and read from the remapped block. The case split that we're doing here is whether or not the bad block happens to be equal to exactly that remapped block, which is the size of the abstract disk, right? So remember that this is the last block of the code disk, or 1 past the last in the abstract disk. That's what I wrote here. 1 past the end is disk size. So why did I do this? The reason why I did this is because we're reading from the remapped block. So it seems sensible that we would use this assumption H bad block, which says that the last, this remapped block at disk size state 2 is the same as the one in the bad block, right? That's where you find the data for the bad block address. But remember that the abstraction relation had this side condition where this remapping is only true if the bad block and the last address are actually distinct. So basically I did this destruct because I can only use H bad block if this equality is false. So you can see, if you jump ahead to the second case under this destruct, that's what we do. It's very straightforward. We just rewrite by H bad block and we're done. The other case is the more interesting one, where we can't use H bad block in this case because the assumption is false, right? So if we try to rewrite by H bad block here, we're going to run into one of these situations where this is not provable. In fact, we have its opposite as an assumption. So that's not the right proof strategy. What's going on in this case is that the user issued a read for 1 past the actual size of the abstract disk. And while we do return the junk data that's in the bad block in this case, that's okay because you're allowed to return anything for an out of bounds read. So the way that we realize this in the proof is this diskette is actually out of bounds. This diskette in the abstract disk is out of bounds. We can do that using Leah. The reason why that's the case is because because of E, right? So if you look at this E hypothesis, it says that the bad block is actually the size of state 2, and getting the size is going to be out of bounds. And then this maybe equals when the left-hand side is none, doesn't say anything, it's just true. So that's how the proof goes in this weird case. And then the other case is just to use hbad block. So again, just to remind you what we did was our abstraction relation, which we carefully thought through, had to separate out this case where the bad block and the last address are the same. So what the proof does is it just does the same split that this abstraction relation does. And actually a very similar thing happens in the other case where we're reading from a good block. Similarly, the hgood blocks part of the abstraction relation doesn't say anything about the last about this case. And so we have to use different strategies in both cases. One interesting takeaway from this proof is that your abstraction relation and your proof strategy have this extra case split that doesn't show up in the code. So the code doesn't have a branch doesn't actually consider whether or not the last address and the bad block are the same. It actually turns out to be correct in both cases, but your proof needs to consider both cases differently because the strategy is different in those two cases. Okay, yeah, we're out of time, and that's all I really wanted to say about this solution.